Okay, now we're back for the final video in this lab. Okay, now this lab, by the way, just a little historical perspective, the first time I taught it, nobody finished in 3 hours. In fact, I don't think anybody finished at all because it was so screwed up. But we've gotten it all straightened out now. You're probably only about 20 minutes into the lab at this point. You figured out the capacitance and you figured out the inductance. All right, so now we're actually going to do the resonance part of the lab. Now, the important thing when you're measuring the resonance is you have to know the resonance frequency. And the way you do that, the theoretical one, is pretty easy to calculate. It's right up there on the board. 1 over 2 pi times the square root of the inductance, L, times the capacitance, C. And what you'll do is you put that in on your spreadsheet under the theoretical. In this case, I've got 345. Your mileage may differ. In other words, I'm probably going to change some of the values of the capacitors and inductors so we get a different curve. But that's okay, because you'll like it. And then it says the experimental. How do we find that one? Oh, we got to do the rest of the lab. That's right. So what we're going to do here is we're going to figure out, based on that approximately, it would say it's 350 or so. Then we would say, all right, we're going to subtract the number, like it says resonance minus 250, so we'd go to say about 100 hertz. And we're going to take our data there. And then it says resonance minus 200, so we take it at, what's that, 150, we take our data there, and so forth. The actual frequencies aren't really all that important until you get close to the actual resonance frequency. If you're off by 5, 10, it doesn't matter. Just round it off to something that makes it easy for you. All right? For once, I'm going to let you round. All right. Greg's got a little bit of allergies, so he coughed. All right. So, we'll go to 100 hertz. How do we do that? Well, we go to the waveform generator, and we go to 100 hertz. We put in 100 here. I left the keyboard on the other side, so I'm just going to guess here where it is about. Well, actually, I only can go to 300. Thanks, Greg. I got to go over there and type it in. Put the keyboard over there in case I need it. All right. So now we can go down to 100. So we'll go all the way to 100. And if we take a look at our waveform, or oscilloscope, that's what we see. What is that? What is it? Well, how did we hook this up, Greg? We forgot to tell him what we hooked up, didn't we?
Yeah.
All right, let's go show him the circuit now. This is the circuit, and it'll be up there in the front so you can see it. All right, we've got the signal generator coming in from the scope over to here, just like we did with the low pass filter, and we've got channel A set up to measure the signal generator signal. Okay. And then we've got the inductor connected to the capacitor, connected to the resistor, and back to ground. And the inductor is hooked up to that signal right there. You can't see it, but that's okay, trust me. And you'll have the board up there. And then we've got channel B hooked up so that we can measure the voltage, the signal across the resistor. Okay. So then what we see is channel A, which is our signal generator, looks like that, and channel B looks like the blue signal. So what we want to do next is we want to adjust channel A until we get 1 volt peak to peak. Right now we're at 500 millivolts per division, so that's 3 volts. That's too much. I might change that voltage, but I'll tell you if I do. Okay? So we bring it down, 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 down. And that's about 1. We can jack that up a bit. And now it's 100 millivolts per division, so it's actually, we can go up a little higher. This whole thing is 1 volt from top to bottom. Now we just go up 1, maybe 2. That's as close as we're going to get. All right, so we got a good signal there. Then we're going to look at the blue signal. We want to expand that up as high as we can. Notice the scale on this is only 20 millivolts. It's a lot lower than the scale on this one, even though the signals look the same. The magnifications, the volts per division are different. So then we do the same thing, but you know, here, we did it all last week where we were trying to figure out the voltage by figuring out the number of divisions, figuring out the, it takes a while, but you can do it, all right? I am going to show you a couple ways that'll make your life a little bit easier, all right? The first thing is we can use these toggles. Let's toggle channel A and channel B. Channel A is going to stay the same the whole time. It's going to stay at 1 volt. Well, we're going to have to keep setting it there. But we want to measure channel B. So we put on channel B and we can toggle channel B cursors. Then we can move it. Maybe we can move it. You hook up, you click on the VB, you put it down at the bottom. You click on the other VB and you put it all the way on the top. And it tells you it's 155 millivolts. Oh, that was so much easier, wasn't it? So much easier than all that crap I made you do last week. Oh, well, too bad. You're used to it. I'm a mean person. All right. So then we would type in 0.155 for our voltage across the resistor. All right. Our signal generator voltage, we could either do it the same way, but we really want to make sure it's 1 volt. And we have our frequency. All right. So then we do it for another frequency, and so forth. But here's the interesting part, something else we can do. If you go to Tools, which is not going to give you what you want, you go to View instead, all right, at the top, and you put this thing on called XY mode. What it does is instead of putting, it puts the X signal is channel A, and the Y signal is channel B. So since they're out of phase, it looks kind of like an ellipse. Sort of like me. I'm an ellipse, right? Okay? What we want to do is get them so that they're in phase, so that as they go together like that, like a straight line. And we can do that. It's not that hard, really. And so what you do is you're going to take data at a bunch of different frequencies, and I can tell you, because we did some experiments on this before, that this particular setup has a resonant frequency at 330 hertz, which I did it the wrong way again. I always do that. 330 hertz. And what you see now is, first of all, look how much bigger the blue signal got. It's not down at 20 millivolts. It's actually bigger. That's important. Okay? It's still not as big as the red signal, and that's okay. But the XY, they're right together, and everything is right in phase. The red and the blue are right together. They have peaks and valleys at the same time. Isn't that wonderful? I think it is. Now, after you get all done taking all this data, remember how I showed you last week how with the filter you could get all your data really fast and really easy and easier way? Well, guess what? We can do that here again too, also in network analyzer mode. Because if we go to hardware, network analyzer mode, and this time we'll go from 100. And remember, your frequencies might be changing from mine. That's okay. Let's go to 500 in linear 10 hertz steps. All right, and we'll set the amplitude somewhere around 50 and start. And this is what your whole plot should look like. Now here's why your frequencies are probably going to change. Because you don't really see the resonance in this, but it's somewhere right about here. It's not as sharp as I'd like it to be. And to make it sharp, we really have to go to a much wider frequency band. So say from 1 hertz up to 5,000 hertz or something like that. But then it's off center, and it won't look as good. I'd like to see the whole thing go like this, like that. Okay? So that's what you're going to be doing. You'll see that with your data, and the capacitance and inductance that you've got should give you a much better resonant curve than mine. And I'll see you in the physics lab.